Okay. So sounds like on recitation, you only got through to 5A. So I will start at the end, jump back to the beginning, and then we'll work our way through with any questions. Right, it likes to do that. Well, pick this. We're just gonna go with this. Yeah, okay. So you can get almost the whole thing on the screen here. We're sharing the right file. Good. Okay. Nope. Come on, buddy. It'd be nice to me today. There it is. Okay. So let's go up. Okay. So this is looking at an example of using atomic primitives. So the atomic primitives that we have covered, there are many. If you're using other ISAs, they will have their own preferred ones. In practice, if you're using x86, you're probably going to use compare and swap, that have some of the same live lock problems. But load lock store conditional is equally powerful in terms of what can express in terms of lock-free algorithms, et cetera, et cetera. So it's a perfectly reasonable exemplar of the different ways that you could actually implement atomic primitives. It's also a fairly cache-friendly one. So we're going to look at a piece of code. It doesn't quite fit on the screen. That's why we're just looking at the text portion. We'll pop down in just a second. That is going to perform an atomic update to a shared counter and then wait for one of two release signals, i.e. it is implementing a barrier pattern synchronization. If anyone is wondering why there are two release signals, this has to do with race conditions. If you have a barrier and it's just on the value of a counter, then you can actually get the thread that releases it getting all the way back to the barrier again before anyone else has noticed that it has released the counter. It's good to have ping pong. There are other ways you can implement it. This is fairly straightforward. Okay, so we're going to look at filling in missing comments and instructions to properly execute the critical section of this. All right, so there are a few missing instructions, and there are a few missing comments. Okay, so let's start with what is already there. So you're loading the location of the release flag. The specification of where everything was given up in the text. So I'm copying the value from the address specified in register 4 into register 7, just making a local copy. Right, so 4 and 3 are arguments, right, to the original function, basically. Is it following the standard way that you would pass arguments? Yeah, not exactly. They're not quite the right registers. Should have been 4 and 5. Does it matter? No. Right. They tell you where they were. Specify anything you want. We're not asking for compliance. Okay, so we're going to check that this is a pointer to a counter. Right. We're going to try to add 1 to something, namely the result of this. And then we are eventually going to try to store this back. So hopefully you can imagine, since we told you wanted to do an atomic update to the counter, that this is going to be if I want to get the current value of the counter so I can add 1 to it, and I want to do this as part of an atomic update, I've only shown you one atomic instruction pair. Hopefully, it should be pretty clear this is LL, right? This is load linked, right? So I'm going to grab the current value with load linked, right? This is my update to the counter value. Right? Told you we were incrementing a counter by 1. Hopefully that's easy to follow. Okay, now this is also clearly a memory operation. I want to atomically update a counter. I have to, update the counter. So what's this going to be? Store conditional, right? Because between here and here, any number of things could have happened. There could have been 5 million years passing, right? It restored from some system update state, after the nuclear war, whatever. It doesn't matter. You have no notion of encoding of time. Right? Anything could have happened between here and here, so we have to conditionally store. Right? See if the value is still known via piggybacking on the coherence protocol to still be in the state it was when we first loaded it here. Okay, so if it is conditional, what do we need to do after we do a store conditional? Check if it worked. Right? So this is a branch. So is it a B&E or a BEQ? Right? So we want to, right, jump back and try again if we failed. Right? So if we failed, which is when the code is 0, we'll do a BEQ. Right? So if in fact store conditional says that didn't actually happen, we're going to go back, we're going to try it again. Right? Now, if we look at the original instructions, we look at the logic that this was supposed to do. It does have some logic that you're going to do on the counter. It's not just an atomic upgrade to the counter. Oops. If this was an atomic update to the counter, that's all we were doing, we would be done here. Right? This has atomically updated a counter when you get to this line. Right? It will keep trying until it eventually updates it. But we actually care about the value of that counter. Right? Care about whether or not we actually got to the number of threads that we're supposed to be waiting. Right? I told you it was a Berry pattern synchronization. So what are we going to do here? The 5 was the number of threads that we're supposed to be waiting for. 6 is the previous value of the counter. It's the old value of the counter. It might be a bug there. Yeah, it's off by 1. So this would have to be n minus 1. All right, sorry, my bad. We'll, don't worry, your exam's a little better sanity check than the practice one. But the logic would still be the same. So if you're not the one that we're waiting for, we're going to jump to waiting. If you are the one you're waiting for, you're going to release. The logic of this, how do you release? About the rest of it, the rest of it's just fixing a race condition. I can just release for the regular old store. Right? I don't need an atomic update to set my release flag. Right? And I know that I don't need an atomic update because I know that only one of me will actually be here doing the release. Okay, and then finally, this is a nice little simple loop. Here I'm just waiting, polling on the release flag locally in my cache. So that's just going to be a BEQ. Okay. But broadly, right, the key things I want you to take away from this sort of question, you can look at how it differs from this. This one's a little longer. Your exam version looks a little shorter, like this. I want to give you at least a couple of examples so you don't overtrain and just think the world consists of nothing but spin locks. Right? There are other things in the world that you might actually want to do with atomic primitives, right? There's a standard pattern you'll see across both of loading a value, right? And then checking that the stored value, in fact, actually succeeded, right? There may be other business logic in here. So for instance, here, right, this doesn't even bother to try to store the lock while it's locked. But this pattern here of attempt to lock, check, go back, try it again, is going to be there in any LLSC pair. Right? The whole point of a store conditional is it can fail. If you do not check for failure, you have a bad pattern. Right? It's not going to work. It's like, conditionally do this. Did it work? I don't know. Right? Yeah, it's not really how you want to make a working program. The other thing I wanted to point out here, right, is that not all updates need to be using atomic primitives. Right? Loads and stores still work just fine. They just don't have the same atomicity issues, right? Now here, the reason we needed atomicity here is I want to get a current value, increment it, and then know that I have done this without anyone else changing the value underneath me before I store it back. Right? Whereas here, I'm just doing a store. Right? The pattern you need the atomic primitives for is a read, modify, write. Right? Here, this is just a write. So this write does actually just happen. So the only thing I need to worry about here would be race conditions, other sort of logic errors. This isn't an architectural fundamental problem with the ISA or the notion of atomicity. This is just, is my code right? So if I have constructed my code so that only one of the people is doing this, then the atomicity is natural. A store happens or it doesn't. But a read, a modification, and a write does not naturally all happen at once. Right? That's what you need actual architectural support for. Right? So anytime you have a read, modify, write pattern. So if you note all of the atomic primitives, they all have that sort of baked into even their name. Right? So you look at other ones, compare and swap. I check two values and conditionally swap them. I have a test and set. Right? So a simpler version, which is only operating on zeros and ones. I have a fetch and fee, where I grab the current value and then put a modification of that value into memory. So fetch and increment, another classic way that you would do a atomic counter. If you had a fetch and increment instruction, I wouldn't do this with 3. I'd just say fetch and increment. Call it a day. Right. So certainly there are ISAs that have done this. Okay. Right. The rest of this is just some business logic wrapped around a use of it. Right. And in general, we will use atomic primitives for some flavor of synchronization. Right? If I am operating on my own data that no one else is touching, I don't need to preserve this sort of atomicity. Right? There's no value to it. Right? So if I'm the only person who has my local variable I in my little for loop and I'm doing I++, I don't need to worry about someone coming in and changing the value of I out from underneath me. I is a private variable. Anytime I'm accessing any shared data, I have to assume that any number of things could happen between any consecutive accesses, and my code still has to be valid for it. Right? So I need some way of building the primitives, like locks, semaphores, barriers, etc., that I'm going to use to actually do synchronization in a shared memory machine. Now, second question. If I had a message passing multiprocessor, is this what I would be worried about? Is this how I would be interacting and synchronizing with others? Leading question, answer no, right? So these are there to allow for concurrency in a shared memory machine, because in a shared memory machine, other people can change your memory values. In a message passing multiprocessor, my memory is mine, right? The way that I synchronize is by sending explicit messages to other people that they then have to wait to receive, process the message, and do something about. Right? So if I want to do an atomic increment in a message passing system, there are lots of different ways you could do that, but you could imagine that there is one entity responsible for holding the value of the counter. Everyone sends them a message that says, I would like to increment the counter. And then it does that when it gets around to it. Right? So the point of serialization is this other process, right, that's running in its own memory space. Right? So you don't have to worry about anything changing underneath. You've handled it all in software. Now, you can imagine if all I wanted to do was to increment a counter, that's kind of expensive compared to go to memory, and most of the time I'm not contending and add 1. Right? This is cheap. So if I'm trying to scale to 4 threads on 1 core, I want to do a shared memory pattern like this. If I'm trying to do a globally distributed system where half my messages don't actually get there, they get there in some random order, right? And then the other half of my messages are actually a Byzantine attack by a Russian botnet. You do things differently, right? So, but it's more expensive. Okay, I was also told that I should probably go over 5 again. I told this was a little brief at the end of the recitation, so again, I'll start here before going through the other questions. So the right way to look at these is to think about the interaction between program behaviors, particular things that we were trying to optimize for, and our choice of coherence protocols, right? So coherence protocol is a choice. Consistency model baked into the ISA, right? x86 is TSO, full stop. Always will be, end of story. What particular coherence protocol does it happen to use to enforce coherence in hardware? You know, pick a different processor, you get different answers, right? This is a microarchitectural feature. But they're optimizations for different program behaviors. So when you're looking at these scenarios, think of this in particular as a bijection between program behaviors and the way that these coherence protocols will interact with them. Why a bijection? Because you could reverse it, right? You could look at a behavior and then analyze the behavior of the coherence, right? Either way would be an equally reasonable thing to think about. Okay, so we have a situation where MESI is better than MSI is better than VI, right? Let's think about what these behaviors, what behaviors differentiate these, right? So where is MESI better than MSI? What optimization did MESI make over MSI? Right? Where does MESI reduce bus traffic? What is the E state good for? What was that? But it's a particular pattern of modification, right? It's not arbitrary modification. It's not going to help me here on my lock, right? Helps me for a particular read-write access pattern. Yes. Right, so E stands for exclusive. So I did a read. I have the only copy, and then I am going to write it. And I don't have to tell anyone about this transition from E to M, because E is sufficient permission to move it to a modified state myself. I don't need global permission to agree to that, because I know I have the only copy, even though it's currently clean. Right? So what is the program behavior that this is piggybacking on? Well, this is if I am reading and then writing my private data, right? So again, fire the compiler writer if I++ is not register allocated, right? But if I am loading my own private variable I, increment it by 1, remember to increment 1, I have to have read it first, right? So if I have a read-write pattern on private data, then no one else will ever have a copy. It'll always go into the E state on first touch, right? On my read, I'll transition it to M, and great, right? Whereas with MSI, first time I read it, it always goes to shared, right? MSI assumes anything I read on first touch might be shared data. That's the only state that it has for it, right? So that pattern is going to play out better in MESI. If I read and then write my own private data, right? Got my own chunk of an array, no one else is going to touch it, right? MSI is going to be paranoid, thinks that everything is shared. It's correct, right? It's fine, but it's doing extra work, right? So that's the case where MESI improves over MSI. Where is MSI better than VI? Right? It's even simpler, right? When there exists read shared data, VI does not know how to share, like at all. VI operates on Highlander rules. There can be only one, right? There can only be one valid copy across all caches, right? So valid invalid is a very simple but obviously correct protocol. If there is only one copy of a line in all of your caches, however many caches you have, then there's no coherence problem because all one copies have the same value. Right? It's degenerate, but sufficient. Right? But it doesn't match a lot of program behaviors. Right? I have some input. My input is read-only. All of my different threads might need that same input in order to do their work. If every time that I want to read something from my input, I have to kick it out of everyone else's cache, that's silly. It's unnecessary. Read-only sharing is fine. If all the values have the same value, right, I can have multiple copies, there's no problem. Right? Incoherence arises if I have multiple copies and they don't have the same value. Right? Coherence is about if I have some memory location, or logically thinking about some variable x living in some memory location, there should be a singular current value of x. Right? This seems pretty basic. If there isn't, it's very hard to reason about what the heck is going on in your program if you can't even understand, that a memory location has a value. Right? That's what coherence is giving you. So I have any read sharing, right? That's MSI over VI. I have read write to private data, right? MASI will be better than MSI. If I only have reading to private data, these are the same. Right? No benefit. If I only have writing to some, even if it's a private output, right? Both these will directly go to the M state. There's no difference. So it's a read followed by write. This EM transition is the only benefit of MESI over MSI. It's dependent on program behaviors. Okay. So take a look at these. VI about the same as MESI, and both of them are better than MSI. All right. So again, let's think about what we know about MESI being better than MSI. Yes. We can go more broadly. It doesn't have to be quite so specific, right? So let's first start with, we know that MESI is going to be better than MSI when you have some read-write pattern, right? We also know that MSI is better than VI if there's any read sharing. So what we also know here is that there's no read sharing, or at least negligible amount of read sharing. They're not sharing any read-only data. And that you are making a bunch of updates to your private data. Right? So if I have a series of read-write to my own private data, I have no read sharing, then I would expect these to both perform pretty similarly. Right? All I do is read and write my own private data. Right? Maybe in the very, very beginning, there was some counter or some index I read at the beginning. There's something I'm going to synchronize at the end, amortize that out across 10 trillion operations. I ignore it. Right? If my common pattern is I only touch my own private data, these will basically be the same. Right? If I have the only copy of my cache line because no one else touches it, then VI is actually fine. Right? If there is no sharing, VI is fine. Right? If I am reading and then writing that data, MESI will also be fine and be better than MSI. Right? But clearly, if there's any read sharing, VI couldn't be there. Right? Better than MSI. Okay. Similarly here, right? This is again simple. Let's assume I have some read sharing. I have no particular read-write access to private data. Right? So it's just all operations on shared data structures. But there is some read sharing. Right? These will be better because they can handle read sharing. This can't. Right? So again, you're keying in on the particular reasons that we're not using, just the one that does the bare minimum. Right? What are the differentiators? Okay, so let's flip all the way back to. Actually, let me very briefly pop out before I continue here. Okay, so there were some people who had some questions about normalization and clustering. I just want to briefly go over. I'm not too worried about you pulling the data out of this one, but it doesn't matter. So let's think about what go all the way back to week 1 and think about metrics. Let's also think about why all the chalk is right here behind the screen. So let's think about what speedup is. All the way back to week 1. What is speedup? Right? Definitionally. I'm recording this. You don't need to take a picture. Okay. So think about the definition of speedup, right? I've got some machine A, some machine B, and speedup, right, of A over B is the performance of A over the performance of B, which is to say we are normalizing our performance, right? So this is a normalized performance value. Speedup is a normalized performance value. That's all it is, right? So normalization is useful because if I tell you, right, the performance of my machine in some particular unit, that's not a necessarily intuitive way of looking at anything. Right? I want to understand how it is relative to some other thing that also exists, usually some baseline machine. Right? So same thing going on here. Normalization, we've just decided arbitrarily that this is our 1.0. Right? So that's our 1.0 on this, is our not taken in order. And that's going to be defined to be 1. Right? In terms of the clustering, right, we're looking at a collection of different options, and we expect the behavior to vary as a function of benchmarks. We want to see how for each benchmark, these different options play out. And we are averaging across benchmarks. We want to think about the average behavior of a design option across a range of potential scenarios. Right? You should get something that looks vaguely like this. Now, what order do you have your series in? Doesn't matter. Right? Yes.
So in the input?
Yeah, so there's it's benchmark number dash branch predictor number dot in order or out order. Yeah. So that's your design space. Right. You can do that the same for all these. Okay. I did get a few questions about that, so I did just want to make sure that I covered that. Okay. Let's pop back to. Oakley dokley. Okay, SimT versus SimD. All right. So where do SimT and SimD diverge from each other? The word divergence here is actually kind of key, right? Because divergence is the case, it basically does cover the cases in which they will differ. Right? So SimD is about everyone does the same thing. I specify that for the entirety of my vector. SimT is, a piece of SimD hardware where I'm going to pretend that every element is an independent thread, and it just happens that they're all being asked to execute the same thing at the same time, so that when I would need different behavior as a function of index, I am allowed to actually do so, right? If I have a set of different branches, if my branches diverge, right? SimT allows you to have a vector of branches. SimD does not. A vector of branches is completely meaningless in SimD. What does it mean to take 32 branches at once if I'm only doing one instruction? I can compute 32 condition variables at once, build a mask out of that, then use that mask to control what happens in the next set of operations, but I basically have to build predication in software, right? So in SimD, it predicates, right? Because it has to do everything. I can mask the behavior so it has no effect, right? But branching is still fundamentally scalar, because SimD is actually also fundamentally a serial single-threaded model, right? There's only one thread execution. It just happens to be wide. SimT is about collecting all the things that are actually, again, by construction, collecting all the things that happen to be doing the same thing at the same time and executing efficiently on SimD hardware. Yes?
We're like taking like the misses property. Do we need to divide that by the total instructions property, or can we just put the misses like this?
It's misses per instruction is the metric you're asked to graph. So you need to divide misses by instructions, committed instructions. Yeah. Okay. All right. The other case that they will diverge is in handling cache misses. Another place that they'll diverge. Basically, any place where the behavior of different threads goes in different directions, right? So for instance, SimT, let's say that one of your threads, most GPUs don't support paging, but imagine you have a one that does, only one of them does a page fault, right? it'll handle that. So if there's any divergence in the memory, any divergence in control. Yes. Thread. Single instruction, multiple threads versus single instruction, multiple data. Yeah. So again, when SIMD is running fast, SIMT is running fast, it looks just like SIMD. But it handles the cases that SIMD is specifically bad at in a different way. And it does that also by having a logically different model, even if most of the time I'm basically just executing wide arithmetic SIMD instructions across a vector. Right? Okay. Anyone have any questions on B? Why, even though GPUs are awesome, we still have not only vector units, but increasingly aggressive vector units on our CPUs? And this goes down to Amdahl's law as much as anything else, right? So getting one instruction's worth of SIMT execution to occur on the GPU takes a lot of effort, right? There's a lot of time to get the data, send it to the GPU across an I/O bus, get the kernels communicated, go through the schedulers. So the GPU has enormous throughput, but there's enormous latency to get that first piece of data out. If all I want to do is multiply two like 4x4 matrices, right? I can do that faster with my own vector instruction set than going and enabling a GPU to compute this minimal amount of work for me, right? The overheads will swamp what I'm asking it for. So there's basically a minimum amount of work that will justify the overhead of bothering to engage the GPU at all. Okay, so the SIMT, this warp level parallelism. What are the other things that GPUs are using, right? What are the other sort of types of parallelism optimizations that they are employing that we have seen for CPUs that are also being used in a modern GPU? Let's start ruling out the ones we know it doesn't use. It is not using out of order execution. Ixnay on the out of order or whatever. I can't do Pig Latin anymore. Cool. You get the idea. Out of order execution is not terribly energy efficient. And it's also very area intensive. No, not using out of order. They're not even employing branch prediction usually. Yes. So that's the first part, but yes. Yeah, so we're looking at things that we've seen talked about for CPUs that GPUs are also using. It's threads and data are basically made synonymous in this. There's pipeline level parallelism. Yep, they are pipeline processors. This is true. Let's go with the simplest version. GPUs are multiprocessors, right? There are multiple GPU cores on your GPU. They don't get bigger just by making the warp bigger, right? You do not have a 10,000 wide warp when you're scheduling your 10,000 threads. That is not how it works. Okay. So GPUs are multiprocessors, and each of these multiprocessors is not just wide, it's also deep in threads. They are heavily multi-threaded. It looks a lot like FGMT, right? So there is a set of warps that have been scheduled. Actually, it's a set of blocks. Each of the blocks is a set of warps. They don't need an independent PC, but you get the same idea. Logically equivalent to FGMT, but again, make them wide. And so that's why they don't even bother usually with branch prediction. They have a fairly shallow pipeline. They have 32, 48, 64 threads waiting to be scheduled. And by threads, I mean, sorry, warps, right? They're sitting there. So every lane logically has a thread ready to be scheduled. And so they're very latency tolerant, right? Throughput, right? So lots and lots and lots of threads, and then lots and lots and lots of cores. And each of these threads is then part of a little parallel warp. Okay. So What are some impediments that would cause the GPU, it's a little awkward here, that would cause the GPU to not achieve the peak possible throughput the hardware would offer, right? So I've got a very, very large number of ALUs, right? If you go look at any NVIDIA marking material, they'll tell you that's how many CUDA cores there are. What they mean is that's how many ALUs there are, right? But that is the maximum possible throughput of the machine, is it could be doing that many flops per cycle, right? What are the things that cause GPU programs to not achieve peak possible throughput? There are lots, so list a few. Yeah. Yeah, so if you have control intensive code, this is not going to happen, right? So if I have control intensive code, some of the threads are going to go one way, some of the threads are going to go the other, and I'm basically cutting my data level parallelism by the fraction of threads that went one way or the other. I have to chop my warps up into and schedule them separately, right? So I will get less utilization. What are other things that prevent it from being peak? Yes. Right, so there are a number of special functional units. So if you are using things that it does not have the full width of, right, it can't do them, right? You do not have as many, cosine units as you do adders. Right? What else? Yeah, so I mean, you can still have pipeline stalls even in a GPU. So they're usually not too bad and handled by a lot of the multi-threading, but if all of the warps that are ready to be scheduled have exactly the same code and have exactly the same dependency, in particular if that read after write is a memory read, right? Then they'll all be sitting there waiting for a load to come back and there'll be nothing to schedule, right? Yeah, so your dependencies can still slow you down. It's latency, it is very latency tolerant, but it's not latency immune, right? So the other thing I mentioned there, memory. GPUs have a memory hierarchy. If everything is going all the way to main memory on the GPU, even though they are very latency tolerant, they don't like that very much. They do like to actually occasionally have a cache hit. It would be nice. Let's go with a very simple one. What if I scheduled a 4x4 matrix multiplication on my 4090? How much of my 4090 am I using with my 4x4 matrix multiplication? Yeah, so if I do not specify a sufficiently data parallel computation, I cannot use it. Right, so the specification of my kernel fundamentally constrains how much of the GPU I can use. What's one other resource I can run out of that might prevent me from using all those ALUs? It's the other thing I need to support thousands of threads. For thousands of threads, I need register state for thousands of threads. So the way the GPU programs work, they do not have a fixed number of registers per thread. They have an allocated number of registers per thread. And so I can actually get a scenario where I run out of registers before I run out of threads. Right, so if I have a lot of local state per thread in my CUDA program, right, I could run out of register space first. Okay. We're fine. Okay, coherence protocol simulation. This is mechanical, but we'll go through it, right? So given a protocol, MESI, MSI, VI would be kind of boring. It's not going to be VI, right? And some mapping of threads to cores and variables to cache lines, right? Then we can simulate some sequence of operations to these variables. So this has already been marked. Note the fact that in this case, A and B are in cache line foo, C and D are in cache line bar. If I am touching cache line foo, there will be no impact on cache line bar, right? Unless they're in the same set, eviction policy, something, which we explicitly said does not happen here. The extra verbiage is to make the problem well-defined and simple. So they map to different sets, so they have literally no interaction with each other. They are completely independent. Okay, so if I load A in MESI, right? So this is thread 0. Thread 0 is on core 0. So we're going to go right here. Initial state for everyone is in I. So let's think about what happens from the perspective of the core and the cache controller, right? So I'm on thread. There's nothing in my cache. It's all invalid. At least these two lines are both invalid. And I want to load A, which is in cache line foo on core 0. So what do? I issue that load to the cache. Cache goes and looks for it locally and says, no dice. It's not here. Right? I don't have a copy of this line. Cache controller goes, okay, I'm going to put a load miss on my bus. Tell the world I am in need of cache line foo. Right? I need to read it. Right? It's going to get a response from memory that says, yeah, here you go. Nobody's got this. It's all yours. And it's going to go to the what state? MESI. We're going to go on a load where nobody's got it on MESI. Exclusive, right? So if no one has this, I have the only copy, it is going to go to the exclusive state. This is going to be exclusive. Nothing else is going to change here. Everyone else is going to go, I don't have this line either. I don't know what you're talking about. It's on the bus. They're going to snoop it. They're going to see it. They're going to, I don't got that line. Okay, so it's going to go to E. I is going to go to E. Great. Done. Thread 1 is going to load B. Okay. The thread 1 is living on core 1. Right. So it's going to go try to look up in its cache for a copy of cache line foo. It's, well, not there. So it's going to go, okay, I'm going to put a load miss on the bus. Say, I need cache line foo. Now, something slightly different is going to happen because core 0 is going to snoop this load miss request and go, oh, yeah, I have a copy. Well, okay. And so that interaction is going to cause it to downgrade to shared. Right? It no longer has the only copy. Right? Just saw that someone else asked for a copy. It's a read. They're both reads. We can do read sharing. That's fine. But E is going to go to S, and this is going to go to S. So again, the stable state after this load miss is this is going to have a copy in S. This is going to have a copy in S. So I'm going to go I to E, no effect. E to S, I to S. Questions? Yes. So A and B are in the same cache line, right? Your cache does not understand what your variables are. Your cache doesn't know what programming language you're running. Your cache doesn't know anything about the semantics of your program, right? Your cache knows what cache blocks are in your cache and whether they are valid, dirty, and what coherent state they're in. So this is, to some degree, an instance of false sharing. There's no actual communication of data. If I'm just always accessing A, you're always accessing B. But if they live in the same cache line, right, they have to co-transfer together. The unit of presence, the unit of transfer, the unit of tracking in cache coherence is a cache line, right? So this is why the layout in memory is very important in parallel programs, right? So your compiler, if you link with OpenMP, it is going to try to lay things out and pad and align accordingly so the things it is trying to have owned logically by different threads, hopefully do not live in the same cache line, right? But it is certainly possible, a little bit there. It is certainly possible that you can have any of a number of lovely flavors of false sharing, right? Okay. So store C, now store C happens to be in bar, so we're not going to involve foo at all. So the first thing we're doing here is a store C. T2 happens to be mapped on core 1. That's living here, right? So we are going to say, I want to store this I look at my cache, it's not there, right? So I'm going to put a store miss on the bus. Everyone is going to go check their cache for copies, say, I don't have one, nothing to do. Memory is going to respond and say, oh, well, I guess you need a copy of the line. Right, again, same reason. Right, why do I need a copy of the line if I'm just storing C? Because I need the whole line. Right, I'm only updating one part of it. Right? And this is going to go from I to M. Right? It's going to go immediately to the modified state. Right? The first access to it was a store. Everyone else is already invalid. If they were in another state, they would have been invalidated. Okay. P0 is stored to A. Again, we're currently in SS. Right? Thread 0 back on core 0. So it's going to go to its cache. It's going to say, hey, I would like to store some value to A. And it gets a response from the cache, says, okay, good news, bad news. We've got a copy of foo. Bad news, you can't write to it. You have insufficient permission. Right? It's in the shared state. So hold on a bit, and we're going to go get an upgrade. Right? And so it's going to put a upgrade miss on the bus. The upgrade miss is going to go out. Right? It is going to invalidate the other copy here. This is going to go S to I. Right? This is going to get the permission to actually perform a write. It's going to do the store, goes to M. Right? Now, imagine a slightly different universe. What would be different if I swapped these two in terms of bus traffic? Yeah, so if I go from E here to M here, and there isn't this intervening sharing, right? That will not cause any bus transaction. I'll be able to do that locally, right? Now, if I swap these, and I'd also swapped my protocol, and this was MSI, and it was only in the S state here, it would look the same. I'd still need the upgrade miss. Yep. That's the case it's winning on. Right, again, I said fairly mechanical, right? Same property going on. Remember that every time you do a store, you will be invalidating everyone else. This is an invalidation protocol. Right? The way that we maintain that there's only one updatable copy is that if you are living in the E or M state, right, you have the invariant, right, that there is only one valid copy of that line. Everyone else has to be in the invalid state. Right? The other thing you'll notice is that we will never get back to E. Right? All the different places it could go are never going to come back to E. Right? The only way to get back to E for foo would be to actually evict the line and come back from invalid in the first place with no one else sharing it. But in this scenario, where we're never actually evicting it from the caches collectively, we're just moving it around between different caches, right? You'll never get that first touch property again, which makes sense. If multiple people are touching it, it's not your private read-write line. Right? This is some shared line for good or ill. Okay. I'll belabor this further. Again, you've got cycle by cycle examples from the recitation slides. Okay. Remaining time, let's go over this. Okay. So let's talk about some shared and message passing multiprocessor generalities. Let's say that I've got a memory system that has exactly one memory location. Is there a difference between coherence and consistency? And if so, what is it? This will not be on your exam, this particular question, but it's good to think about. All right. A little too specific to redo for the exam, but so if I have exactly one memory location, then the logical serialization of a memory location is the logical ordering of all memory operations, which is what consistency is concerned with. So they're actually the same in this degenerate case. So if I have a one memory location system, consistency and coherence are the same. And also, I don't know what I'm doing with a one memory location system. It's not sure I can do much with it. But it would technically be the same. right? So as soon as you have multiple locations, right, these begin to diverge, right? Coherence is that there is an agreement on the order of updates, that there is a logical timeline of the sequence of values that a particular memory location has taken over time, and then you can map your reads into that timeline, right? So you could get an older value, right? That's still possible, certainly, in coherence, right? But that just means that logically, this happened before whatever update actually got applied, right? There is no, you're never going to read a value out of sequence, right? You're either before or after some update has applied. Whereas with with consistency, as soon as you have multiple locations in memory, right, you might see different places observe different orderings among when those updates occurred, and you may no longer have a singular logical point in time that everyone can agree has actually happened, right? This is a challenge you start to get into with consistency modeling, right? You have to go out of your way and do a little extra work to get some sort of global ordering on all events. It's not naturally there just by enforcing the coherence on each of the locations. Because I could think we're at the point where X has been updated 3 times, and you can think that you're at the point where X has been updated twice, and that would be fine, except you could also think that you're at the point that Y has been updated 20 times, and I think Y has only been updated once, right? So now we don't have a logical common point in time, right? And we need to make our parallel programs work despite this, right? So we tend to have some explicit synchronizations to occur when we want to actually agree collectively on a mutual point in time having actually happened, right? Okay. This feeds then into part B. So bus-based snooping, unsurprisingly, doesn't scale. It doesn't scale to have a single point of serialization. It is a large wire connecting all of your cores, right, which everyone locks down until they are done performing the operation on it. So a more scalable pattern is something called directories, right? Where I will have a point of serialization, but it will be for a subset of the entire memory space. So usually the more cores that I have, the more directories that I have, and each core is going to take 1/n of the total space. Assuming I'm doing powers of 2 and the banking is easy. So again, think of this like banking. Okay. So why is this still going to be fine for coherence? Part 1, right? So if I partition my address space and I say there's a little lookup table next to core 0, and it covers the first 16th of the address space, why am I still going to be able to do coherence here, even though I've lost my global bus ordering? And why does this not cause a problem? Why are directories going to still work? The glib answer is that, like everything else in computer science, you can solve something with a sufficient application of indirection. Directories are an indirection. That's not really the point we're worried about here. Again, coherence is concerned with one memory location. As long as all of the traffic for one memory location goes to the same place, I still have my serialization point, I still have my ordering, I still have all of my coherence properties. Everything will go to that directory, just as everything would have gone to the bus, right? I won't necessarily get the same ordering I got before, but I will get a total ordering on all of the updates to a particular location, right? Because they're all going through this one point in the system. Okay. Now, this obviously follows from what I was just talking about previously for A. My consistency job with directories has, however, gotten a little more interesting, right? So now if all of my updates to X go to one place, all of my updates to Y go somewhere else, right? The potential drift in ordering among all the participants is going to expand, right? Right. So if I have partitioned my memory into a bunch of different locations, and it may take literally a different amount of time to even send an update, right, to different addresses that you're operating on, to reach the directory and then come back, right? You can imagine that the common notion of time will play out rather differently than with a single global point of serialization in your bus-based system, right? So it won't change the consistency models, it will just make them differently expensive to implement, right? This is the right way of looking at it, right? If I want to enforce some particular ordering, I have now made it easier for things to get differently or unordered with respect to each other. Enforcement costs are going to go up. Okay. So most machines, there are some exceptions, use hardware coherence. Right? There are machines that are just fundamentally incoherent, the Xeon Phi, for instance, the raw microprocessor. But hardware coherence is not actually necessary, right? It's not strictly necessary, right? Again, if I can write a piece of software that emulates a piece of hardware, ergo, software could do anything. This might do it 100,000 times slower than it would have, if you actually had hardware to do it. So let's think about, however, the challenges in using software to provide coherence. Why might we want hardware to do this job for us? Right? What are the challenges going to be if we were wanting to delegate this software? What mechanisms that are already there in the software would we likely be able to leverage, right, in order to provide a coherence protocol implemented in the software? Certainly when people were building logically shared memory machines with multiple physical disjoint pieces of hardware, they've done this. This is doable. But there are some fairly obvious challenges. So what does software currently manage with respect to the memory system? Where does software get involved in our memory management? Does software manage your L1 cache? No. Right. Software manages what is or is not in main memory. Software manages your virtual memory system. Software manages that virtual memory system in terms of pages. Software and cache lines are not natural partners. In fact, software has a very difficult time even understanding how cache lines work. The ISA may have some cache flush instructions, but your software can't go in and directly manipulate, right, a cache line level granularity set of state. There's no interface for it because the cache is microarchitectural. It's not architectural. It's not defined. Right? So if I want to do my coherence in software, you might have some fundamentally incoherent hardware to start with, right? I can do this, right? But the granularity of operations is going to be necessarily larger, right? I am not going to want to do cache line level or variable level coherence. It's going to be very, 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 very slow, right? Because again, think about that snoop check. Think about all the things that have to happen. These sort of global agreements, if I want to do them in software. I want to avoid as much of that as possible. Right? So if you think about where this is sort of a natural thing to be done, you can look at this where this actually occurs, as I said, hierarchically in systems that people have built where part of the system has hardware support, but then they're gluing multiple of these together with software. They do that with NUMA and the virtual memory system, right, where they basically treat those main memories as a software managed cache. So if you're looking at any sort of fine-grained sharing, this would suffer, right? It's really a function of granularity. Right? Again, software can do anything you want as long as you can tolerate how long it takes for software to do it. Right? So given that it's going to take software a while to do it, you want it to do it for a lot of data at once. I'm doing coherence at gigabyte, large pages. Yeah, sure. Right? It's either there or it's not. Right? Pretty easy. Right? And if most of the time it's not actually actively being shared, again, also fine. Right? So if I can have my TLB give me enough information, right, that the translation is my coherent state, I'm fine. Right? If I want it fine-grained, no, not going to happen. Again, try to differentiate the possible versus the engineering costs associated. Right? Not a particular singular answer I'm looking for. Right? Mostly just looking at questions of scale. Right? And there's a sharing. Okay. We have enough time for more. And then any final questions? So this should be pretty straightforward, especially if you have your notes. Right? So if I have an initial state, I have an action, right? So if I'm currently in the invalid state and someone else is doing some remote store, I'm still in the invalid state. Nothing interesting is happening here, right? If I'm in the shared state and I locally do a load, that's just a hit. I'm very happy. Life is good. If I am in the M state and there's a remote load, right? I need to send, not only do I need to downgrade myself to the shared state in MSI, I also need to send a copy of this line across the bus. I have a potentially more up-to-date, almost certainly, in fact, more up-to-date version of this line. I need to give it the current contents of this line, put that on the bus so that everyone can get one common, up-to-date, shared copy of this line. Right? So I need to do a bus transaction to respond to this request for remote load with, oh, I've got the current data, memory doesn't. Let me get that for you. If I have in the shared state and there's a local store, right? I do not have permission to do the store. I'm going to need to put on the bus and upgrade miss and get the permission to do so. I have the value. I don't have the permission to actually write it. Other questions in the remaining 8 minutes? Yes. Yes. Yep. Go out this afternoon. Number 3? No. Number 3A is overly specific. Right. So if you think about what these are broadly asking about, that's definitely in scope, right? So they're looking at what are some of the differences between coherence, consistency, how do different ways we implement them affect one or the other, right? But the degree of depth, these are going deeper than we would in a timed exam. So, yes. Will question 2 be of the same length? It will not be longer. Yeah. So another way of answering the question about question 3. Question 3 may see a new life as multiple choice questions. Conceptual questions, coherence, consistency. Yeah. I haven't gone over any particular problems with consistency because consistency is hard. In particular, if you're looking at problems involving consistency, they're mostly about understanding the design space of possible reorderings, race conditions, and other really, really nasty stuff. And mostly I just want you to understand that terrible things can happen. I don't need you to actually be able to do debugging of multi-threaded code in a timed exam. Right. So also, I don't want you to have to think about, well, MIPS is sequential consistency, so you don't have to worry about where to put your M fences because it's sequential consistency, but hard enough as it is, right? Okay. Any other questions? Alrighty, once more unto the breach on Thursday, and then that shall be all she wrote.